In particle physics, we are dealing with lot of interactions of particles, maybe charged or uncharged particles. So for a reaction to take place, it should obey certain conservation rules or conservation laws. We already discussed about conservation of charge, linear momentum and angular momentum. Now let us consider the conservation of baryon number. So let us consider a reaction, a proton interacting with another proton. Three particles are produced in accelerators by the interactions of small particles, mainly protons or neutrons, anything like that. Okay. Normally, protons are used in an accelerators to produce another particles. But this reaction P plus P plus pi is 0. This reactions is possible according to the conservation of linear momentum, angular momentum and charge. But when we observe, this type of reactions never happened. Pions are normally produced in the accelerators by the interactions of protons. But this is the reactions appeared very frequently. That is P plus P bar gives pi plus, pi minus and pi 0. So this is a very frequent reactions for the production of pions. So what is the reason which forbidden this reaction? That is P plus P gives pi 0 plus pi 0 plus pi minus. So when we observe certain reactions, it is restricted, even though when we observe this in the terms of conservation of linear momentum, conservation of angular momentum and conservation of charge, a lot of reactions are possible. But naturally, they are not occurring. So reason for this difference is that. So the reason for the non-occurrence of certain reactions which are possible by conservation of linear momentum, angular momentum, charge, etc. are due to the presence of the conservation of some more quantities. So when we observe, when the scientists observe these reactions, they find that another quantum number, which is known as the baryon number, should be conserved in reactions. So baryon number is a quantum number. Okay, for all baryons we assign a baryon number plus 1, and for all antibaryons we are assigning a baryon number minus 1, and for non-baryons we are assigning a baryon number is equal to 0. So for all baryons, baryon number is plus 1, and for all antibaryons baryon number is minus 1, and for non-baryons the baryon number is 0 is assigned. So when we observe the reactions or the possibility for a reactions when on the consideration of baryon number, we find that most of them are most of the reactions which are occurring naturally, or all of the reactions which are occurring naturally, are obeyed by the conservation of baryon number. That is, baryon number, total baryon number before interaction should be equal to total baryon number after interaction, and this is known as the conservation of baryon number. So the baryon number of the left hand side should be equal to baryon number of the right hand side. Here the baryon numbers are scalar quantities, their addition is also scalar addition, just numbers are added. Suppose here for protons baryon number is 1, and for antiprotons P bar is antiparticles of proton. So its baryon number is -1. For all baryons, baryon number is 1. For all antibaryons, baryon number is -1. So the total baryon number on left hand side is 1 minus 1 is equal to 0. Here pi plus baryon number is 0, pi minus baryon number is 0, pi 0 baryon number is 0. So total baryon number is 0 plus 0 plus 0 is 0. So 0 gives 0 means the baryon number is conserved in this reaction. So what about this reaction? Here proton baryon number is 1, and for proton baryon number is 1 because protons are baryons. Baryons have a baryon number plus 1. This pi 0 pi plus pi 0, their baryon number is 0 because they are all non-baryons. So they are mesons. So the baryon number, total baryon number is 0 plus 0 plus 0 is 0. So in the left hand side it is 2 and in the right hand side it is 0. So it is not possible. So this reaction is not possible because it is not obey the conservation of baryon number. So that is the non-occurrence of this type of reaction in an accelerator. So this reaction is always like this. P plus P minus gives pi 0 plus pi minus plus pi 0. And the reason for is the conservation of baryon number. So baryon number should be conserved in all interactions. And the meaning of baryon number is always conserved means baryons are created and disappear in pairs. When a baryon comes to the world, an anti-baryon must be born along with it. It need not necessarily its specific antiparticle. So when a baryon is created or comes to the world, associated with it an anti-baryon is also formed. Also, when a baryon is disappeared, similarly an anti-baryon is also disappeared in such a way that the total number of baryons minus the total number of antibaryons is a constant thing. So total number of baryon minus total number of antibaryons are conserved in our world. That number is a conserved one. Okay. So baryons and antibaryons are created in pairs. Let us discuss about the conservation of lepton number. So we know that lepton have three families: electron family, muon family and tau family. Okay, so lepton number is also conserved, should also conserved in reactions. But unlike baryon number, lepton have three lepton number, that is electronic lepton number, muonic lepton number and tauonic lepton number. So the electron, muon and neutrinos always appear and vanish in particle-antiparticle pair. So we know that in a pair production, photon is converted into an electron and positron. So they are produced in pairs. So pi minus gives mu minus plus antineutrino, muonic antineutrino. Okay, so this is the decay of pions. So how the pions are decayed is pi minus gives muon plus an anti-muonic neutrino. Muonic neutrino. Okay. So conservation of lepton number means this lepton number Le notate for the electronic lepton number or lepton number for electron. So all the electrons and electron neutrino, okay, have electronic lepton number +1. So for electron family we have a lepton number, it is known as electronic lepton number. Similarly a muon family have a lepton number that is known as muonic lepton number. Similarly tau family have a lepton number that is known as tauonic or tauonic lepton number. Okay, so they should be separately conserved. That means for electrons and electron neutrinos, Le, the electron lepton number, otherwise electronic lepton number is +1, and its antiparticle, that is positron plus anti-neutrino, electron anti electronic neutrino have lepton number is equal to -1. So L is equal to -1 for positron and this anti-electronic neutrino. So for all other particles, whether it is a lepton or muon or tone, its electronic lepton number is 0. Okay, so electronic lepton number is 0 for all other particles. Okay, similarly, muonic lepton number for muon and neutrino or related to muon is +1, and lepton number for anti-neutrino and mu plus is -1, that is anti-muon, and for all other particle muonic lepton number is 0. Then similarly tonic lepton number is +1 for tau minus and mu tau, and L tau is, that is tonic lepton number is -1 for tau plus and anti-neutrino. Okay, so the lepton number separately conserved. So electronic lepton number, muonic lepton number and tonic lepton number should be conserved in all interactions. Okay, so for example, let us discuss this reaction, that is mu minus, this is mu minus, gives electron plus anti-electron neutrino plus muon neutrino. So this is mu minus. Okay, so for mu minus, L mu is equal to, for muon L mu is +1, for electron L mu is 0 plus electronic anti-neutrino L mu is 0, and for muon this is 1. So 1 plus 1, this is muon lepton number is conserved. Then what about electronic lepton number? So that is for muon electronic lepton number is 0. So 0 gives, for electron it is 1, and for anti-electron neutrino it is -1, and for muonic neutrino it is 0. So we will get 0 is equal to 0. So these interactions obey the lepton number conservation principle. Okay, so these reactions are possible on the point of view of lepton number. So the lepton number and baryon number conservation law governs the creation and destruction of all the all the non-fermions, that is half integral particles. So the creation and destructions of all fermions are governed by the lepton number conservation and baryon number conservation rules. Okay, so let us discuss another conservation law in particle physics, that is conservation of strangeness number. So what is a strangeness number, or what is a strange particles? So strange particles are particles which are showing some strange behavior. For example, lambda, sigma, psi, omega and k particles are strange particles. So when we discussed the classification of particles, we discussed that lepton have 3 families, that is electron, electron neutrino, muon, muon neutrino and tau neutrino, and have its antiparticles. So 6 particles and 6 antiparticles. And one thing is important, that the number of leptons are a constant. There should be no addition or subtraction from this number. But the numbers of mesons and baryons are not a constant one. Okay, we are studying, we study only certain hadrons. Okay, so its number, whether it may be a meson or a baryon, its number is not a constant. There are lot of mesons and baryons present in our universe, but we study only important mesons and baryons. Okay, that about, but its number is not a constant. There are lot of mesons and baryons are there, but we study only only important mesons, and we study about only the important mesons and baryons. Okay, so here k particle is a mesons, and lambda, sigma, psi and omega are baryons. Okay, they are important particles. So what is a strange behavior? Normally hadrons means both mesons and baryons. Normally hadrons are formed by strong interaction and they are decay by strong interaction. So that is the normal behavior of a hadron. Its formation and decay by strong interaction. But in the case of certain particles, they are even though they are formed by strong interaction, they are decayed by weak interaction. So that is a strange behavior, and the particle which obey this type of behavior is known as the strange particle. For example, kaons, lambda, sigma, psi, etc. are example of strange particles. And the formation time for that type of particles, this type of strange particle, is 10 raised to minus 22 seconds. So that is in the order of strong interactions. And its decay is decay within the time interval of 10 raised to minus 10 seconds, means they are decayed due to weak interactions. So this type of behavior is known as the strange behavior. Strange particles, there are a lot of strange particles in baryons, and the strange baryon is known as hyperon. Hyperon is a group of particles which are baryons and they are showing the strange behavior. So the strange baryon is known as the hyperons. Okay. Also the strange particles are created in pairs. Okay. So pi minus plus p gives lambda 0 plus k 0. So there is a pair of strange particle. Lambda is a strange particle, k is a strange particle. So this is known as the associated production or associate production. Or pi plus plus p gives k plus plus sigma plus. So p minus plus p gives k minus plus k0 plus pi 0. So they are produced in pairs, or this type of production is known as the associate production. So they are produced in pairs. So there is another quantum number which is known as the strangeness quantum number is present in the case of a strange particle, and its number is different for different particles. Strangeness quantum number is different for different particles. Certain number is assigned for certain strange particles. Okay. So and the strangeness quantum number is conserved in strong and electromagnetic interaction. An important thing is that the strangeness quantum number is conserved only in strong and electromagnetic interaction. But in weak interaction, its strangeness number is strangeness number of the initial interacting particle and product particles by change by 1 unit, that is delta S is equal to plus or minus 1. That is, in the case of a weak interaction, the strangeness quantum number changes by 1 unit. Okay, that is the conservation principle of strange. That is the conservation of strangeness. That is that about the conservation of strangeness quantum number. So it is conserved only in strong and electromagnetic interaction and not conserved in weak interaction, but they are changes by 1 unit in the case of a weak interaction. So the number assigned for the particles are strangeness quantum number assigned for the particles are for k plus and k0 particles, strangeness quantum number is plus 1, and for its antiparticle strangeness quantum number is minus 1. That is, k0 bar is antiparticle for k0 and k minus is the antiparticle of k plus, and its strangeness quantum number is minus 1. And for lambda family, strangeness quantum number is minus 1. Okay, so when we think about particles, these two are antiparticles. So just Let us discuss about particle only. For K family, its strangeness quantum number is +1. Okay, K plus and K0, its strangeness quantum number is +1. For lambda family, strangeness quantum number is -1. For sigma, its strangeness quantum number is -1. So all the multiplets, that is sigma plus, sigma 0, sigma minus, have the strangeness quantum number -1. And for the psi family, that is psi 0 and psi minus, have the strangeness quantum number -2. And for lambda particles, have the strangeness quantum number -3. Okay, so not the lambda particle, the omega particle have the strangeness quantum number is equal to -2. So lambda, sigma, psi and omega have different strangeness quantum number. All its quantum numbers are minus. Okay, so the hyperons have the strangeness quantum number minus number, that is -1, -1, -2 and -3. Okay, so let us discuss more about quantum numbers in next class. Okay.